I'm going to talk today about some progress we've been making on a CubeSat soft X-ray imager for studying the lunar exosphere. Now, this work goes back, or the story behind this work goes back to the mid-1990s when the Röntgen satellite, ROSAT, which is an astrophysical X-ray observatory, looked at Comet Yakutaki, as you can see on this slide. And ROSAT observed, surprisingly enough, a copious amount of soft X-ray emission from Comet Yakutaki. And this was a mystery at the time. X-rays are usually associated with very hot objects, and comets are, of course, cold, balls of ice. Why would you get such a tremendous amount of soft X-ray emission from a comet? Well, the answer was eventually given by Tom Cravens at the University of Kansas. And the reason why you get such intense X-ray emission from comets is because of a process called solar wind charge exchange, SWCX, pronounced SWIX, soft X-ray emission. And the way solar wind charge exchange soft X-ray emission works is that high charge state solar wind ions, for example, oxygen +8 in this view graph here, this example, although it doesn't have to be oxygen +8, it could be high charge state iron or neon or any of the many heavy species in the solar wind flow. But a high charge state solar wind ion interacts with a cometary neutral, in this case hydrogen, steals an electron from the cometary neutral, and ends up, in this case, as oxygen +7, but not in the ground state, but in an excited state. And what happens is when this excited state relaxes, a soft X-ray photon is emitted that can be detected at astrophysical observatory like ROSAT or XMM or Chandra, or any of those. Now, this is a process that has been well established at this point, and in fact it occurs wherever the solar wind interacts with neutral gas. And as you know, there are many places in the heliosphere where the solar wind interacts with neutral gas. One place, for example, is at the Earth, in the Earth's magnetosheath. The Earth's exosphere extends out beyond the magnetopause, and when the solar wind in the magnetosheath interacts with the terrestrial exosphere, soft X-ray emission results from this process. And this has been observed, like the cometary X-ray emission, by many different astrophysical observatories, and we can, with the appropriate instrumentation, image the magnetosheath, that is the solar wind interaction with the Earth's magnetosphere, in soft X-rays. We can do this, though, not just at Earth, but we can do this around other planets like Mars and Venus, and in fact those observations have been made, and we can do it at the moon. As people at this meeting know, the moon has a very tenuous atmosphere, but it has an atmosphere, and the solar wind can penetrate very, very close to the moon, actually hit the moon, in this case. And our colleagues at University of Kansas, Tom Cravens and Ina Robertson, I guess it's been 5 years ago now, simulated this process, the solar wind interacting with the lunar exosphere. You can see the reference down here. It was a GRL paper from 2009. And the conclusion that Ina Robertson and Tom Cravens made in that paper was that the soft X-ray emission that would result from the solar wind interacting with the lunar exosphere would in fact be intense enough to be observable. So What we did at this point is we went back and we looked at some old ROSAT observations of the moon, saying, well, you know, Tom and Ina say that this is observable, but can we actually see evidence for this in the ROSAT image of the moon? So we took the ROSAT raw data, and I should mention at this point that the work I'm talking about here has been published. The reference is right here. It's been published in JGR Planets. And if you're interested in the details, I refer you to that. I won't go into the details on this plot. But the bottom line is that we can observe the solar-wind interaction in this ROSAT image, the solar-wind interaction with the lunar exosphere, and we see it as this limb brightening signal right here. And actually, it ends up being quite intense, 11 keV per centimeter squared per second per steradian. And furthermore, this is scientifically important too. It's not just a curiosity, because what it allows us to do is it allows us to probe using soft X-rays the lunar exosphere, and not just a particular component of the lunar exosphere, but the total column density, including all species of the lunar exosphere. And again, I refer you to the JGR Planets paper. And in that paper, we compare the observations to various models, and we managed to determine scale heights and other important aspects of the lunar exosphere from these observations. So if we had, for example, a CubeSat or something in orbit around the moon making these observations, we'd be able to learn quite a bit more about the global structure of the lunar exosphere. But in order to do that, we'd need a wide field of view soft X-ray imager. And a couple years ago, we flew exactly that, a wide field of view soft X-ray imager, as a piggyback on a suborbital mission called DXL, diffuse X-ray mission from the local galaxy. And you can see we flew a prototype wide field of view soft X-ray imager here, looking out the back of the rocket. And this was a very successful flight, and we were able to establish that a wide field of view soft X-ray imager would be able to detect this soft X-ray emission from the solar wind lunar exosphere. And in fact, this prototype instrument was successful enough, the data were encouraging enough from this, that we gained confidence that we could do it even with a CubeSat, a 3U CubeSat telescope. And this shows some of the actual flight data from the DXL Storm instrument. So the poster I'm presenting here at this meeting details the progress we've made on this wide field of view soft X-ray CubeSat imager over the past year. Most of the poster details a lot of the material that I've talked about in this presentation. This part I'm showing on the screen right here is the lower right corner of the poster, and this shows some images of the progress we've made on the CubeSat imager. You can see up here, this is our 3U CubeSat imager. The optics is up here at the front. The optical element here has a 5 by 5 degree field of view and focuses soft X-rays onto the detector plane, which is back here in the instrument. This right here is the electronics board with boards, it's a stack of boards with the detector plane at the front. That's this assembly right back here. To keep stray light from getting into the CubeSat, we've developed a telescoping sun shield, which you can see right here, that simply mounts on the front there and is spring-loaded and helps keep stray light out of the instrument. The optical element here is a square-pore, square-patch slumped microchannel plate, which, as I said, is shown down here in the lower right. It's got many small 20 micron by 20 micron square pores in it. Those of you who are familiar with microchannel plates that are used for detecting particles and photons, it's the same principle as those microchannel plates, but those microchannel plates have circular pores. This has square pores for focusing soft X-rays, and this optical element goes right on the front there. So we've made some pretty good progress. This, of course, focuses on the instruments part of the CubeSat, and as you know, with CubeSats, a major challenge with the CubeSat is, of course, the avionics. So I guess that covers pretty much what I wanted to say in terms of a preview for the poster. My name is Mike Collier. I'm at NASA Goddard Space Flight Center. So if you have any questions or you're interested in this and would like to chat with me about it, please drop me a line. Thank you very much.